Bismillahirrahmanirrahim. Assalamu alaikum students. Our today's lecture is about binary adder and subtractors. We know that most of the digital systems like digital computers perform variety of uh, information processing tasks, and from those tasks we can say that various arithmetic operations are encountered for different functions and operations. The basic arithmetic operation is addition of two binary digits. The simple addition consists of four operations which produces the possible elementary operations consist of four possible elementary operations which are, we can say that 0 plus 0, and we use annotation here, then we can say that 0 plus 0, 0 plus 1, 1 plus 0, and 1 plus 1. These are the four possible elementary operations which are performed, and out of these four, three operations produce a sum of one digit. That output is equal to 1. Output is 1, either it is 0 or 1. And as these three operations, first three operations produce the output, or we can say sum of one digit. But when both the organ and addend are equal to 1, then the output produced is the binary sum consists of two digits. You can say the two digits equal to, you can say, will be equal to 1 0. 1 0. The binary, as it consists of two digits. The higher significant bit of this result is called a carry bit. And so we, as it is mentioned here, the higher significant bit is called a carry bit. When the organ and addend numbers contain more significant digits, the carry obtained from the addition of the two bits is added to the next higher order pair of the significant bits when there are more number of bits. As here in this example, we consider only two bits which are added. But when there are more number of bits, then the carry bit is added to the higher significant order bits. And a combination circuit that performs the addition of two bits is called the half adder. Is called half adder, which only produces the significant addition of only two bits is called half adder. One that performs the addition of, and so if we increase the number of bits, and the uh, combinational circuit which will perform the addition of three bits, two significant bits and a previous carry is a, that will be a full adder circuits. The names of the circuits uh, which we are using here as half adder and full adder, from the fact that two half adders can be employed to implement a full adder circuit. And similarly, a binary adder subtractor is a combinational circuit that performs the arithmetic operations of addition and subtraction with binary numbers. That we should remember that these operations are only performed for the binary digits, binary numbers. We have developed, we will develop. Okay, there was a problem with the internet connection, so I will repeat some portion of this discussion. That when we used only two bits, that to add up, and the binary sum consists of two digits, the output will be on two digits. The higher significant bit of this result is called carry. When the organ and addend numbers contain more significant digits, the carry obtained from the addition of two bits is added to the next higher order pair of the significant bits when the addition is more than, consists of more than two bits. A combination circuit that performs the addition of two bits is called half adder circuit, as we have mentioned in this example. and when the number of bits are increased, we can say the one that performs the addition of three bits, two significant bits, and a previous carry is a full. Then it will be a full adder circuits. The name of the circuits from the fact that two half adders can be employed to implement a full adder circuits, and we can say that a binary adder-subtractor is a combination circuit which will perform the arithmetic operations of additions and subtractions with binary numbers. We will use only binary numbers, digits in these operations, and we will develop the different circuits of these hierarchical designs. First of all, we will design a half-adder circuit uh, by means of a hierarchical design. Half-adder circuit is carried out first, which we and then we will use these half-adder circuit to develop a full-adder circuits. And so we can say that in the figure you can see the table of a half adder circuit. From the we can say explanation of a half adder, we found that the circuit needs two binary inputs, as the circuit needs two binary inputs x and y, and two binary outputs, which will be carry bit and a sum bit. C denotes the carry and S denotes the sum. And according to the operation, we will see the input variable designate the organ and addend bits. The output will be sum and carry. We assign again the symbols to inputs x and y, and symbols of outputs will be C and S. C for carry and S will be for the sum. The block diagram we will see in the next slide. Here we can see the operation, and that Boolean function for the two outputs can be obtained directly from this truth table. That we can see that the carry output is equal to 1 only when both the inputs are 1. And we can say that it's an AND circuit for two inputs. In the case of AND gate, we know that the only output is equal to 1 when both the inputs are high or equal to 1. So C will be equal to x into y, and we know that S function is equal to 1 when one of the two inputs is equal to 1 and both inputs are different. We can say that it's an exclusive OR circuits which is going to be used here. The simplified sum products expressions are so here are S is equal to x prime y plus x y prime, x prime y plus x y prime, and C is equal to x into y. So the logic diagram is shown here in the implementation of half adder circuit. We for the two outputs can be obtained directly from these expressions which we developed from the truth table. The logic diagram of half adder implemented in sum of products form by using simple S and carry is shown in this figure. That's sum of products. And the two products are being summed by an OR gate, and the S output is we obtained, and C is obtained by ending both the inputs. And it can also be implemented with an exclusive OR and AND gate, as shown in this B part of the implementation of half adder circuit. That X and Y are exclusive OR, and which will give us the output of some bit output bit, and X and Y are ANDed, which will give us the carry output by ending the both of the inputs. And this is the implementation of half adder by using those equations derived from the truth table. And these forms of half implementation of half adder circuits, which are shown in these different two forms, we can show that the two half adders can be used to construct a full adder circuit. Full adder is a combination circuit that performs the arithmetic operation of three bits. As we can see that here, X, Y, and Z, we consider three bits are used to add up. It consists of three inputs and two outputs. Three inputs are labeled as X, Y, and Z, and outputs are carry, and some outputs are labeled here. The two outputs are necessary because the arithmetic sum of three binary digits ranges in value from 0 to 3, and binary 2 or 3 needs two digits, that we need two digits to show the output. The two outputs are designed by the symbols of S for sum and C for carry. The binary variable S gives the value of the least significant bit of the sum. S will give the value of the least significant bit of the sum, and C will give the most significant bit by the C. Give the output carry, and that will be the most significant bit for the last operation which will be used. And we can see that there will be 8 number of operations performed in this uh, full adder circuits. And in the this truth table, you can easily see that 8 different combinations of inputs will be used. As we know that 2 raised to 3 will be equal to 8. Okay, from these 8 combinations of inputs, the output variables are determined from the arithmetic sum of the input bits. So from the arithmetic sum of these input bits, we will find out the output variables. When all input bits are zero, the we can say all input bits are zero, the output will be is zero. S is equal to zero, and C is also equal to 0. When all the input bits are 0, the output will be 0. The S output is will be equal to 1 when only one input equal to 1, or when all the three inputs are equal to 1. We can see that the S will be equal to 1 in these 4 combinations when one of the three inputs is equal to 1, or when all the three inputs are equal to 1. For these 4 combinations, the output S will be equal to 1. The C output has a carry of 1 if 2 or 3 inputs are equal to 1. C is a carry bit, and it will be equal to 1 when 2 of the inputs are equal to 1, or when all the 3 inputs are equal to 1. So for these 4 combinations, you can see that the carry is equal to 1 when y and z are 1, or x and z are 1, or x and y are 1, and for when three of the all the three inputs are equal to 1, the C is equal to 1. The input and output bits of the combination circuit have different interpretations at various stages of the uh, problem. We will be discussed in our next slide. Uh, the binary signals of the inputs are considered binary digits to be added arithmetically to form two digits sum at the output. And we also can see that for a different combination, the same binary values are considered as variables of Boolean functions when expressed in the truth table, or when the circuit is implemented with logic gates. And the map for the output full adder circuits, we can see that from this truth table, we can construct the functions. We can say the output functions for these two output bits of sum and carry, and these functions from the truth table we can see that will only for some bit there are four ones, and these are placed in the k map here, one, and these are the for the four input combinations of min terms. And similarly the z, so we can say the C carry output is also equal to 1 for the combinations when we will consider those four combinations for which the C bit is equal to 1. Okay, from the table we draw maps for full adder and place that those ones for the given input combinations of the min terms, and from these ones we find out the functions for the S output term and the X S. This is the function for the sum output bit, and this is for the carry simplified version of the function of the carry output bit. From these functions, simplified functions, we can easily implement the full adder circuits with the by using the expressions from we which we get from these maps easily. Okay, this is the implementation of full adder circuit in the form of sum of products, and this is for the sum output bit, which is equal to the sum of products. Products of is obtained by using these four AND gates, and sum is by using this OR gate. And this is for the implementation of carry bit output, carry bit, which is equal to the also sum of product. Both the products are gained by using AND gates, and sum is obtained by using the OR gate. By using these implementation, we can easily find out the output of the given circuits which we have obtained, and from these implementations, we can easily find out these, and we can also implement the full adder circuit in the form of by using two half adder circuits and an OR gate, which is another implementation of the full adder circuit. Full adder by using these two half adders and then OR gate, also known as the carry look ahead adder. Carry look ahead adder in this implementation of full adder by using these two half adders and one full adder. Okay, we will see that, and this circuit is equal to half adder, first half adder, and this is equal to second half adder, and an OR gate is used for obtaining the carry output. The sum bit of the first half adder is going to the input of the second half adder, and the third bit is added as the second input of the second half adder, and from those that half adder we obtain the sum bit, and the carry bit is obtained by using the carry bit of the first half adder is OR with the carry bit of the second half adder, and the carry is obtained. We can see here the S sum bit is equal to Z exclusive with X exclusive of Y, and we can obtain the same function, and carry bit is obtained by using the exclusive functions of X and the Y, as we can see here that that this carry bit is equal to the, here we will get X into Y, and at this point is the, we can see the combination of the X exclusive Y, X exclusive Y, and then it is ended by the third input of Z. And that output will be equal to this thing will be added with the this thing, and we will get the our carry output for the carry look ahead adder. This is also known as the carry look header, and this is the implementation of a full adder with two half adders and an OR gate. Now a binary adder, we can also say that it's also called a ripple carry adder, and binary adder is a digital circuit that produces the arithmetic sum of two binary numbers, and it can be constructed with full adders connected in the cascade form as shown in this figure. And full adders are connected in a cascaded form with the output carry from each full adder connected to the input carry of the next full adder in the chain. You can see that the output carry is connected to the input carry of the next, as we can say that and this is a full adder circuit with two binary inputs and one sum output and one carry output with a input carry. We initially we can assume it's said C naught 0, and the output carry of first adder is has become the input carry of the next full adder in a chain, and the output carry of second full adder has become the input carry of the third full adder, and the output carry of third full adder has become the input carry of the fourth full adder circuit, as shown in this diagram of that interconnection of four full adder circuits to provide a 4-bit binary triple carry adder. 4-bit binary triple carry adder, as we have mentioned that binary adder is also known as a triple carry adder because of the construction with full adders are connected in the cascaded form. And from the truth table, we can see that the script input carry and script that C naught, C1, C2, C3, four full adders which are connected in the cascaded form. In these four full adders, we have seen that the for the C naught, C1, C naught is equal to 0. Input carry for the first full adder is 0, and A naught and B naught in A naught, B naught is equal. These are the values of A naught and B naught, which produces the 1 plus 1 is equal to 0, and this will be the C1 carry output carry, which will be the input carry of the second adder, and by adding these three we can say that 1 plus 1 plus 1, the output sum will be equal to 1, and the carry will be also equal to 1. This one is forwarded to the next full adder circuit, and from that next full adder circuit we obtain the sum is 1 and carry is equal to 0, and this carry is forwarded to the fourth stage. You can see that the C3 the third carry of the fourth full order, and we have added, and this output is obtained as shown in the 4-bit full adder circuit. The bits added with full address starting from the, as we have started from the least significant positions, we can say subscript zeros are obtained. The 4-bit adder is a typical example of a standard component, and it can be used in many applications involving arithmetic operations, such as observe that the design of this circuit by classical method would require a truth table with the 2 raised to power 9, we can say that 512 entries, since there are 9 inputs to the circuits, we can know that the 9 inputs 2 to 4 to 6 to 8, and this is the ninth inputs to the circuit. So there will be 512 different input combinations. By using an iterative method of cascading a standard function, it is possible to obtain a simple and straightforward implementation. And that for that straightforward implementation, we will see that carry propagation that we have considered. The addition of two binary numbers in parallel implies that all the bits of the augment and addend are available for computation at the same time, as we have to the know that any combination for any combination circuit, the signal must propagate through the gates before the correct output sum is available in the output terminals. The total propagation time, we know that every gate takes some time to propagate the signal from the input to the output. The total propagation time is equal to the propagation delay of a typical gate times the number of gate levels in the circuit, that how many gate levels we have used in the circuits, and the propagation time, which is equal to the propagation delay of the any typical gate. The longest propagation delay time in an adder is the time it takes to propagate through the full adders, since each bit of the sum output depends on the value of the input carry. The value of sum at any stage, given stage in the adder will be in the steady state final value only after the input carry to that stage has been propagated. And we can say that the output will not be accurate until and unless the input carry is propagated at that stage. In this situation, we can consider that the output is of the final stage. We can say that S3 uh, is as shown in the previous figure. We can say that in this that S3 will be uh, obtained when inputs A3, B3 are available as soon as input signals are applied to the adder. However, input carry C3 does not settle to its final value until C2 is available from the previous stage. And we know that similarly C2 has to wait for C1 and so on down to C0. Thus, only after the carry propagates and ripples through all stages will the last output S3 and carry C4 settle to their final correct value, and they have to wait for the previous carries to settle down. So these propagation delay, we can say the carry propagation, the number of gate levels for the carry propagation can be found from the circuit of the full adder. We can found that how many gates are used and we can calculate the propagation delay. The circuit, we can say that can be redrawn as the propagation rate will affect out the output signals on different times. So signals are uh, given enough time to get the precise and stable outputs. And we can see the most widely used technique employs the principle of carry look ahead to improve the speed of the algorithm. And that carry look ahead we have used also in the to make the full adder by using two half adders. These this is the full adder with P and G shown as the output uh, propagation outputs of the given gates. We have find out that the number of gate levels for carry propagation we can find out and calculate that how many number of gate and how many stages are used to construct a system. The input and output variables we use the script I for the output and input variables. The signals at PI and GI settle to their steady state values after they propagate through their respective gates. That these signals will be settled down after passing out through their the respective gates. And these two signals are common to all full adders and depend only on the input organ and addend bits. The signal from the input carry Ci to the output carry Ci plus 1. Right? Signal from the input carry Ci to the output carry Ci plus 1 propagates through n, which is AND gate, which is going to propagate through an AND gate and an OR gate. These two gates, the carry signal is propagated input carry propagated through these two gates, which constitute two gate levels. We can say that two gate levels are in the way of the input carry. If there are four full adders in the adder, the output carry C4 would have 2 into 4, 8 gate levels from C0 to C4. If there are 4 full adders are connected, so C will have to propagate through 8 gate levels C0 to C4. For an n bit adder, there are 2 into, and there will be 2 into n gate levels for the carry to propagate from input to the output level. So we can say that different for the Boolean function, the carry propagation time is an important attribute of the adder because it limits the speed with which two numbers are added. As speed is dependent upon the propagation of the carry. So although the adder or the for that matter any combinational circuit will always have some value at its output terminals and the outputs will not be correct unless the signals are given enough time to propagate through the gates connected from the inputs to the output. So we know that the output will not be correct unless the proper propagation time is not given to the gates to process. through the combinational circuit. Since all other arithmetic operations are implemented by successive addition, the time consumed during the addition process is critical. An obvious solution for reducing the carry propagation delay time is to employ faster gates with reduced delays. However, physical circuits have a limit to their capability. Another solution we will suggest, as we know, that is suggested is to increase the complexity of the equipment in such a way that the carry delay time is reduced, and there will be several techniques for reducing the carry propagation time in parallel adder. The most widely used technique employs the principle of carry look ahead logic. Carry look ahead logic, which we have used in this circuit when we use half adder to construct a full adder circuit. And by using these techniques, we know that the steady state value of any output state of the adder circuit, as we have full adder circuit, if we consider full adder circuit previously, in this circuit, Pi is will be equal to AI exclusive with Bi, and that Gi will be equal to Ai into Bi. These are the steady state values, and output sum and carry, which will be obtained by using Pi exclusive with Ci input carry, and the output carry will be equal to Gi plus Pi into Ci. These are the mentioned that how the outputs are labeled at the given diagram. We can see that Pi is the output of the sum bit of the first half adder, and Gi is the carry output of the first half adder, and similarly Si and Ci plus 1 are the output sum and output carry bits for the full adder circuit. In Gi is carry generate, Pi carry propagate, and C naught is the input carry. And so from these equations, we can easily find out that C1 will be, when we put the 0 state, C1 will be equal to G naught plus P naught C naught, and we will find out, we can say that the G is called a carry generate, and it produces a carry 1 when both AI and BI are 1, regardless of the input carry. That CI will GI will propagate, is a carry generate will produce one carry regardless of the input carry bit. And similarly, because it determines whether a carry into stage I will propagate into stage I plus 1, that is whether an assertion of Ci will propagate to an assertion of Ci plus 1. And so by using these equations, we write down the Boolean function for the carry output of each stage and substitute the value of each C from the previous equation into the next equation, and we obtain the final output carry equation. And the C3 does not have to wait for the C2 and C1 to propagate. And here we can see that the C3 is finally equal to G2 plus P2 into G1 plus P2 into P1 into G naught plus P2 into P1 into P naught into C naught. So we can see that C3 by using these uh, implementation, we know we can see that C3 does not have to wait for C1 carry and C2 carry to propagate, and it will be generated as soon as the outputs of the stages are obtained. And we can see that the construction of 4-bit adder with carry loop adder scheme easily in this logic diagram of carry loop add generator is, we can see that C3 is propagated at the same time as C2 and C1 are propagated. So if each sum output requires, we can see that two exclusive OR gates, the output of the first exclusive OR gate for the 4-bit adder carry loop head. In this 4-bit adder, we use the carry loop head scheme, and we see that the if each sum output requires four requires the sum output requires two exclusive OR gates, and the output of first exclusive OR gate generates the PI variable, and the AND gate generates the GI variable. This exclusive OR gate will generate PI, and the AND gate will generate the value of the GI. And from these, the carries are propagated through the carry lookahead generator and applies as input to the second exclusive OR gate. All the we can say the all output carries are generated after a delay through two levels of gates. Thus, outputs S1 through S3 have equal propagation delay time. The two-level circuit for the output carry C4 is we can say is not considered here. This circuit can easily be derived by the equation substitution method. We can substitute the equation and we can easily find out the 4-bit adder as shown in this a 4-bit adder with carry look ahead. We have seen that the input carry is used to generate the sum bits, and then the C1 is used for S1, C2 is for S2, C3 is for S3, and C4 is generated. At the same time, all the carry bits are generated as the output bits, and some bits are generated for the function of the given circuit. And Boolean, we know that Boolean function for each output carry is expressed in the form of sum of products form, and each function can be implemented with one level of AND gates followed by an OR gates, and these functions we can find out the carry output bits by using the different functions. And we see that for a binary subtractor system that how the subtraction of unsigned binary numbers can be done most conveniently by means of complements, as we have already discussed in chapter number 1, it's section 1.5. We have discussed that how the two numbers are subtracted by using the complemented form of the subtractant number from the given, and detail of this we will see in the our next lecture. So take care, students. Inshallah, we will see you in the next lecture. Take care. Allah Hafiz.